we've discussed elements around planning, discussing the statistical analysis plan, and we discuss issues around details that we need to include in our proposals, and also discuss data management. And today we're discussing our discussion is around statistical analysis itself, but the focus is on the development of scripts, analytical scripts. And as you can see, in terms of the focus for this webinar series, the focus is really on how to build transparency in our processes. So it's not necessarily, as I said, as I've been emphasizing a number of times, it's not getting into the nitty-gritty details around the different statistical methods themselves, but how do we build transparency in our methods, and how do we build rigor in our processes, so that we can build more confidence in the work that we do. And we started off by describing how we need to describe the detail that we need to include in our proposals, and also looking at statistical analysis plans, which inform our thinking in terms of writing of proposals, obviously informed by the research question, and how that it translates into the design of the project, but also discussed how approaches to data management that ensure that our data are secure, our data are we've got robust data processes in terms of managing our data. And today we are focusing on statistical analysis, and really statistics are the primary tool for assessing relationships and evaluating study questions in quantitative research. And we know that statistical tests are designed for specific types of data, and with that they carry particular assumptions, and we need to be aware of those particular assumptions. And we won't be able to get into those assumptions today into detail, but we'll just highlight some important assumptions that we may need to consider. But importantly, whenever we study about the different methods that we may apply in our research, then we need to understand those assumptions as well, so that we can apply our methods better. However, there is misuse in terms of the statistical methods that are applied, and this may be inadvertent, or it may be due to ignorance or lack of planning. And sometimes it's as a result of researchers trying to achieve a particular result. In a review, articles reported that about 50% of articles in medical and dental research contain one or more statistical errors. And this is a problem. This is a huge issue, in that the research that we're presenting has errors, and what does that mean? What is the implication of that on the results and the findings that we make from the studies? 72% of articles lacked statistical validation for their conclusion, meaning that there is a lack of connection between the results that are demonstrated in the article and the conclusions that are reached. And also importantly, I mentioned earlier the issue of assumptions, and it is important that we discuss the assumptions of the tests that we apply in our statistical analysis, and that is largely absent in many research articles. And this statistic here shows that about 90% of all published articles that were evaluated in this particular research, they lacked any discussion around statistical assumptions. So how do you know that the test is actually doing what it is supposed to be doing if you haven't tested the assumptions? And also in the context of what we've been talking about, which is really to improve transparency, if you're not discussing those assumptions, how do we know that the results that you're presenting in your research are valid? So this is something that is extremely important that we need to think about and that we need to always keep at the back of our minds as we apply these statistical methods. We need to understand what they are testing, and we also need to understand the assumptions that they carry with the tests that they are doing. All right. In a cross-sectional study in a faculty of students from colleges in medicine, these researchers, they reported that 53% or 54% thereabout found statistics of the sample, found statistics to be very difficult. About 53% could not correctly define the meaning of p-value. About 37% ill-defined the standard deviation, and over 50% failed to correctly calculate sample size. I spoke about the calculation of sample size yesterday, and I'm going to emphasize the importance of sample size again today in terms of hypothesis testing and why it's important. And as I've been emphasizing throughout the 3 days that we've been doing, or the past 2 days that we've been doing these webinars, the low level of skills among researchers, inadequate knowledge is one of the biggest drivers of this. And we're not seeking support from statisticians, but also we know that we don't, and especially in our context in low and middle income countries, we do not have sufficient number of statisticians and biostatisticians that we can call out to that can help us with our research. So this creates a problem in terms of our research, and it raises questions about the quality of the research that we're producing, and which is why we've been doing these webinars to raise this awareness and to make sure that as researchers, we approach our research with a heightened level of sensitivity towards the methods, towards the processes that we engage in with respect to our quantitative research. So, what steps then should one follow when one approaches their data analysis? And generally, and others may, come up with additional steps. These are the general steps that I follow when it comes to statistical analysis. And the first step is always exploration. And this is assuming that I've already, performed my data management. All right, I've already, cleaned my data. And this, it's not a once-off. Data management is not a once-off process, but even during analysis, you continue to do that. And this process of data exploration can also lead me to data cleaning, additional data cleaning that I may need to undertake. Obviously, the next thing that you need to do is to describe your data, and that is what descriptive statistics is all about. And if you're interested in making inferences from your sample about the population from which the sample is drawn, then you perform inferential statistics. And then once you've performed your inferential statistics, then you need to go back and assess whether your models that you have performed, they do not violate the assumptions about that particular model. And I will demonstrate, I'll do a live demonstration of what I mean about that. All right, just to start us off, I thought maybe let me just give some definitions about what we're going to be talking about. And the first definition is about statistics in general, which is the mathematics of the collection, organization, interpretation of numerical data, especially the analysis of population characteristics by inference from sample. Again, all of these elements that we've been talking about over the past 2 days, including today, are included in the definition of what statistics are. So if you're talking about what statistics are, it's not only about the analysis that you are performing, but it is also importantly about how you organize your data, which is informed about how you collected your data and the thinking processes that you applied before you get to that stage. And also importantly, as it says here, the statistics that we are running, we're interested in making statements about a population, and we're making those statements from a sample, all right? So it is important that we understand how our sampling approaches influence our ability to make inferences from the sample about the population that we want to make statements about. So the next level of statistics is what is called descriptive statistics. And usually in papers in epidemiology or around or any studies that deal with human studies, quantitative studies, you want to describe your sample. You want to describe your demographic characteristics, and if you are measuring any clinical characteristics, you want to describe those as well. All right. So you're describing based on the characteristics of the variables that you have collected. You will then summarize your data in a convenient and in a presentable way, and also informative. And we'll discuss a little bit later what that means. And then you also have what we call inferential statistics, which, as I was just saying earlier, that is really about the inferences that you're making about a population from the sample. It's not always possible to measure every member of a particular population that you're interested in. And populations can be extremely large, and you're interested in drawing a sample, and based on that sample, you want to make inferences about the particular population. And you're interested maybe in estimating a parameter. It may be a mean, it may be a median, or it may be a proportion. For example, you're interested in finding what is the average height of children, preschool children in a particular environment. Let's say in a rural, underprivileged environment. What is the average height of those children? And how does that average height compare to a non-standard? Are those children growing better, or are they growing poorer compared to how they're supposed to grow, for example, compared to the World Health Organization standards for children from birth to 5, as well as the references for children from 5 up to the age of 19 years. All right, and so inferential statistics is really about this estimate, which is the proportion or the mean or the median, and sorry, okay, I think I'll discuss it a little bit later, discussing a little bit more about what inferential statistics is about. So the first step, like I said earlier, is this, concept of exploring the data. And it is really about assessing the characteristics of the data, and you would, perform, you'd assess the distribution of the data, you'd assess outliers, and for assessing distribution, you may use histograms, which will tell you about the skewness and the kurtosis of the data, as well as the spread. And there are also statistical tests that can help to tell you whether, for example, the data are normally distributed or not. Many of the statistical tests may require that the data have a particular, one of the assumptions of those tests may be that, for example, they require a normal distribution. And so before you perform your t-test, and you want to see whether your data are normally distributed or not, so that you can compare, you can compare with confidence the groups that you are comparing, for example. And these are what are called parametric tests, which have got more stringent assumptions about, about the tests that they're running. But there are also options of non-parametric tests. So if certain assumptions, for example, around symmetry and normality are violated, then there are available tests that you can apply, which will help you in your analysis. And unfortunately, I'm sorry, again, I'm not going to go into those details, but I will show you some of these tests. I've got a slide that shows you some of these tests. Getting into the details of the test is a subject of another day. You may also be interested to exploring whether there are outliers in your data which may influence the parameters that you obtain from your models. You may also be interested in exploring whether they are missing, they're missing data, and so that you can know how to deal with those missing data. And also sometimes before you make decisions about how you build your model, you may be interested to assess whether there are certain relationships, say for example, between your independent variables. So one of the assumptions of a regression model, for example, is what we call multicollinearity. You need to avoid multicollinearity, all right? And that is variables that are correlated with each other. And so by simply running a pairwise correlation, you'll be able to assess whether any of your independent variables or your exposure variables are related, and that helps you to make decisions about how you approach your analysis. I will show an example of that with some analysis that we did for a particular study. All right, and these are just some of the, like I said, some of the graphs that you may perform to explore your data, such as your histogram, which shows the distribution of your data and whether there's symmetry or there's no symmetry. And there are certain characteristics about a normal distribution, and such as, for example, it is a bell-shaped, as you can see on this graph. There's a symmetric distribution about the mean, and the mean and the median will coincide. So one of the one of the ways that you can thumb suck whether your data are normally distributed or not is if your mean and your median are the same. If they are similar, then you can say with some level of confidence that your data are normally distributed. And obviously, but it's not only about the spread, but also about the kurtosis, the thickness of your distribution. All right, and these are just cases, examples of skewness, of data skewness, where you've got, for example, a positively skewed distribution with weight, and a lot of biological characteristics will have this kind of skew, and you have a negative skewness as well. Salary also has a positive skew, where you have a lot of individuals having a lower salary and a small number of individuals having being in the higher salary bands. If you're considering, for example, certain lifestyle diseases, you may find that it tends to skew the age. It tends to skew towards older individuals. All right, and you've got fewer young people that may have that particular condition. All right, and again, this just demonstrates the relationship of these three measures of central tendency, which is the mode, the median, and the mean, and how they relate in the different types of distribution in positive skewness as well as in negative skewness, with the median being smaller than the mean when there's a positive skew, but and the mean being smaller, and the mean being smaller than the median when there's a negative skew. And you can use this, like I said, when you are looking at your data and you're doing your data exploration and you just run a summarization of your data, and you compare your mean and your median, then you can see, okay, how much by how much do they differ, and which one is larger than the other, and then they can tell you, give you insight in terms of the potential distribution that you may find in your data. These are the measures of central tendency that we use when we're describing data, continuous data specifically, all right, or numeric data. We use these measures of central tendency, and that is the mean, the median, and the mode, all right? But also, we don't only describe data in relation to the value, the measure of central tendency, but also in relation to the spread, because it is possible that two samples can have a similar mean but have different spreads, and that may influence your results. All right. So we're not only interested in the estimate, which is the mean or the median or the mode, but we're also interested in finding out how it is distributed, how the data are distributed around that particular estimate. And generally, when you're presenting your mean, you will present it with a standard deviation. And when you're presenting your median or your mode, your median, you present your interquartile range and your range. And if you're presenting your mode, you present the range. All right. And choosing this obviously is very important. Choosing the type of summarization that you're going to use, or the type of descriptive statistic that you're going to use, is very important. And your data need to be summarized in a manner that ensures that important features of the data are not lost. And we've spoken about the shape of the data as we're talking about the distribution, but also you need to consider the variable types. I mentioned yesterday, if you've got a categorical variable which has been coded using numbers, such as 1, 2, 3, for example, you cannot then summarize them with a mean or a median. It is not meaningful, all right? So it takes away that summarization does not is not intuitive and does not, and it takes away the important features of the data. All right. So, and you need to summarize the data to adequately represent location and the spread in data. As I showed you in the previous slides, your mean and the median and the mode will differ depending on the distribution of your data. If you add an outlier to your data, if there's an outlier, rather not to add, if there's an outlier in your data set, the mean will be very sensitive to that, whereas the median is less sensitive to outliers. And whether you remove or you keep the outlier, the median is not going to change by much. But when you remove, but when there's an outlier in your data set, if you remove it, that may drastically influence the value of the mean compared to when you keep it. So in a particular case where you've got a true value, you've got true values, but those values are outliers, or you've got this very skewed distribution, it's not a good thing to present your data using a mean, because, like I said, the values of those extreme values will influence the mean, and it is better to present a median. And like I said earlier, when you're presenting the median, you present it with an interquartile range or the range, and you may present the mean with a standard deviation. So these are important considerations that you need to make when you are going to summarize the data. Also, in terms of variable type, if it is so as I was saying earlier, in relation to point number 1, if it is a categorical variable, then you want to summarize it using a proportion or a percentage. And this is just like I've showed you the slide. I showed you this slide yesterday, which helps you to decide how you're going to summarize your data. And here we've got different types of variables. So we've got numeric variables and we've got categorical variables. And then we've got subcategories under the numeric variables and subcategories under the categorical variables. So you've got your discrete variable is one. Okay, let me start with the nominal. The nominal is where you've got two options, categorical options, two groups. It's either yes or no, dead or alive, survived, or did not survive, diseased or not diseased. All right. So you've got those two groups, and and then in discrete, you've got three or more groups, but in discrete, there is no order in terms of there's no hierarchy in terms of the groups that you have. In other words, no one group is better off than the other. So, for example, you can be looking at races or ethnicity. You're looking at 4 ethnic groups, and there is no hierarchy in terms of the groups. Or you're looking at eye color or hair color. You've got brown hair, you've got black hair, you've got blonde hair, you've got maybe another type of hair. If you've got those 3 groups, hair color does not infer any advantage. So no one hair color infers any form of advantage compared to the other. So they're all on the same level. There's no hierarchy. All right. But sometimes, and the ordinal sometimes falls in this category here as well as categorical, but sometimes you can also analyze it as a as a numeric variable, and I will explain the different cases where that can happen. So if an ordinal variable is one where there is hierarchy, say for example, you're looking at the severity of disease, you're looking at mild, moderate, and severe. So for those 3 categories, I mean, you've grouped your sample or your patients according to only those 3, according to those 3 characterizations of severity of disease, 1, 2, and 3. In this particular case, it does not make sense to summarize them using your median or your mode. All right, sorry. But here you might want to summarize them using your proportions. Now, the difference between the discrete and the ordinal is that there is a level of hierarchy between the groups. The ones with a moderate disease are worse off compared to the one with a mild disease, and the one with a moderate is better off compared to the one with a severe condition or with a severe disease. So there's a level of hierarchy in terms of how, in terms of the disease severity. But in some cases, for example, when you are rating, which also form part of ordinal data, so you've got a rating scale from 1 to 5 or from 1 to 10. In that particular case, you can summarize your ordinal data using your medians, all right? Especially when it comes to ranking, all right? You can use your median and count data, as the name suggests, is the number of items. For example, the number of individuals who are enrolled in a particular faculty, for example, that is count data. And that can be, or for example, the number of conditions one has, all right? So you've got a sample of about 100, and you're looking at the number of lifestyle conditions that individuals have been diagnosed with. And somebody will say, I was diagnosed with diabetes, I was diagnosed with hypertension, and I was also diagnosed, let's say, with some cardiovascular disease, some cardiac disease. And so you've got 3 different types of disease. So my disease count in that particular case would be 3 because I've got 3 different conditions. Somebody else may have 1 or 0 or two, or and so on. Right. So and those can be analyzed or summarized rather using a mean or median or mode. And also you've got continuous data, and these are data that can take up any value in a particular range. So for example, your height and your weight, your blood pressure measurement, your blood glucose measurements, those are all continuous variables, and they are summarized with either a median or a mean or a mode, depending on the factors that we've just we spoke about a few minutes ago. And that's the distribution. All right. Now, when we're making inferences, we're interested in the sample parameters of the proportion, and and we estimate. So it's about two inferences. So inferential statistics are about two inferences, and that is the estimate itself, which is either a proportion or a mean or a median, and the range at which it may be found. A sample suggests that a plausible value, which is a proportion or a mean or median, is found in a particular range. And that particular range is called a confidence interval. And sometimes we work out a confidence interval, the 95% confidence interval, or the 99% confidence interval, or a 90% confidence interval, which tells you that if you would, 95% of the time, you would find that if you're looking at the 95% confidence interval, it tells you that if you would resample 100 times, 95% of those times, you will find that estimate between those two values. All right. And the information from the sample is then used to determine whether the population parameters is a particular value, as in you're comparing to a standard, or whether two samples come from the same population, you're comparing two different samples or different samples, and you want to see if they're equal. And this is performed using this concept of hypothesis testing. I'm not going to get into too much detail about it, but okay, that's a repetition. And so just a little bit about the confidence interval. It's a range in which we expect to find the true value. All right. As I said earlier, if you've sampled 100 times, 95 of those times, you expect that the estimate will lie between those two values, the lower limit and the upper limit. And I've shown you, I don't mean to get into the details in terms of these equations, but I'm just showing you, just leading up to what I'm going to be talking about later on, in terms of the importance of sample size in determining your confidence intervals. This is the confidence interval of the mean, and this is the lower limit, and this is the upper limit. The larger the sample size, and this goes back to the importance of calculating an adequate sample size for your particular question, which is determined by the effect size that you want to establish. All right, sample size will influence these parameters, both for the mean as well as for the proportion. All right, and so I said earlier that inferential statistics uses this method of hypothesis testing, which is a method used to draw inferences about a population from a sample. And it involves making a tentative assumption about a parameter, which is the null hypothesis. So there are two hypotheses that you will be testing. Maybe you've heard about the null hypothesis and the alternative hypothesis, which are completely different. So the null hypothesis is a hypothesis of no difference, and the alternative hypothesis is a hypothesis of difference. So you're saying, for example, there is no difference between the two groups in relation to whatever characteristic that you are measuring, all right? Compared to the null hypothesis, which is there is a difference. So you are saying, in other words, that the difference between those two groups does not differ from zero. Whereas in the alternative hypothesis, you're saying that that difference is significantly different from 0. And as I said, these, when one is completely true, the other is completely false. Now, in hypothesis testing, there are 4 scenarios that we're likely to encounter. One, the first scenario is where the null hypothesis is true, and we accept the null hypothesis. So we say the null hypothesis is actually true, and we accept that. So we're saying that there is no difference. All right. And so in this particular case, you're saying this is a confidence that you have. All right. It's 1 minus alpha. In some tests, we set alpha at 5%, and that is a significance level. So, but we're saying 1 minus alpha will be, if you're setting it at 95%, for example, will be 5%. We're saying one could be 95% confident that there is a 95% confident that this result is true. All right. So that's the first scenario. All right. The second scenario is that the null hypothesis is actually true, meaning that there is no difference, but you wrongly reject the null hypothesis. And we set sometimes at a level of, let's say, 5%. So we want to be 5%. The chance that we may be wrong, we set it at 5%. And that is what is called a type 1 error. That occurs when you've got a large sample size. So when you've got a large sample size, you're likely to encounter this scenario. So if it's too large, all right, you're likely to encounter this scenario, and you may find a difference that does not necessarily mean anything. There's a concept of statistical significance versus clinical relevance, for example. So a difference, if you've got a large enough sample size and you've got 2 groups, and the mean blood pressure in group 1 is 120, and the mean blood pressure in group 2 is 122. With a large enough sample size, you are able to find a statistical difference between those 2 groups. But is that necessarily a clinically relevant difference? If it was a difference of about 10 units in terms of blood pressure, then maybe you would say that is both clinically relevant as well as statistically relevant. But sometimes it may also be that you find this difference of about 10 units in terms of the blood pressure unit, which places the other group in a prehypertensive state. All right. So if the one group is 125, the mean is 125 units of blood pressure, and the other one is 135. Group 2 can be categorized as being prehypertensive, all right? And if you've got a small sample size, then it's possible that you may be unable to detect that difference, and that is what is called a type 2 error, and that occurs. So we set the power, and that occurs with the probability of beta, all right? And so what we usually do, we set the power as 1 minus beta. So you may want to set your test as 1 minus 0.2, which is 80%, or 1 minus 0.1, which is 90% power, all right? And this is a case where you're able to correctly reject the null hypothesis, all right? And so I think I've gone through all of these different scenarios. So going back to the emphasis on sample size is that you need to have a sufficiently large enough sample size to avoid both type 1 and type 2 error. And a larger sample size is important. It leads to increased precision in the estimates of various properties of the population. Apologies for that. And this yields to more sensitive hypothesis tests with greater statistical power and smaller confidence intervals. So this is extremely important, again, just overemphasizing the importance of sample size. And I'm not going to go into those details about the sample population in the sample. You can read through this, but I just want to show this slide here, which shows the reliability of your results in relation to the sample size and how that increases with increasing sample size. But obviously, you can't perpetually increase a sample size that is limited by budget, but it's important before you start your research to establish what sample size you require for your particular study. And all right, and and that will also help you to satisfy Gaussian conditions of of the Gaussian distribution. And you may apply these methods, such as summarizing using a mean and standard deviation, and performing your parametric tests. All right. Now here, this is just a table. I'm not going to go into detail on this table, but this will be available to you. But what this table does, it just shows you the different scenarios that you may encounter in terms of your research question, and the different tests that you may use. Firstly, the summarization, as well as the different tests that you can use to test, for your hypothesis test. For example, if you've got one sample, and this, and the sample follows this normal distribution, you can use a one sample to test. But if it doesn't, you can use a Wilcoxon test. And if you are comparing a proportion to a value, you can use a binomial test. If you are comparing two groups which are not paired, this is also important. So in terms of groups, you can have groups which are paired, meaning, for example, an example of a paired group is when you measuring the same individuals before and after an intervention. Let's say there's an exercise intervention and you're interested in seeing levels of blood pressure before and after an exercise intervention. All right, and you measure your participants before, and you find the values of blood pressure for each individual, and you measure the same individuals after that dietary or exercise intervention. Let's use a dietary intervention. It's probably more intuitive. After that dietary intervention, then you assess your blood pressure again, and you see whether there's been a change in blood pressure. All right, that is a paired scenario. All right, so for that you use a paired test. But if you've got two independent groups, though, different individuals classified by, for example, diseased or not diseased, and you want to compare the characteristics of those groups, then you will use a Mann-Whitney test if they fulfill or the assumptions of a Gaussian distribution. But if they don't, then you will use a Mann-Whitney test. All right. And to compare two proportions, you may use a chi-squared test. All right. There are scenarios where you're interested in comparing more than two groups, three or more groups, and these are the different tests that are available for variables which follow a Gaussian distribution. And if they don't follow, then you can use a Kruskal-Wallis test. And for proportions, you can use a chi-square test. And there are other tests as well that are listed in this table. So this just gives you a way of when you think about your question, then you can come to this list and think what are the potentially relevant methods that you can use in your scenario. But obviously, there's a lot of consideration that needs to happen in terms of how you apply those methods. And this is what we've been emphasizing. You need to consider the assumptions of each test and what it really assesses, so that you can ensure that your test does what you want it to do, and what you're presenting is actually robust data or robust results from your test. All right. Now, yesterday we spoke about the elements of the different tools that I've introduced you to, such as your data management plan, such as your analysis plan. And I said today we're going to be discussing the important elements of an analysis script, and I'm going to show you an analysis script shortly. All right, but importantly, your script needs to be clearly formatted. It needs to be orderly. So, and there's a set particular order in which which is, useful in terms of presenting your analytical process. You start with data management, you follow with exploratory analysis, you follow with descriptive analysis, and then you follow with with inferential statistics. And then after that, you assess the assumptions, whether your data have not violated any of the assumptions of the tests that you have performed. So that is a very useful order in which to organize your analytical script. And importantly, in line with the principle of transparency that we've been emphasizing, all the steps that you have followed, they need to be outlined in your script. And not only the steps, you need to have notes that explain why you're doing what you're doing. So these are the important elements that these are the three elements that I think are important in having in your analytical script. And I will show you an example. And the example relates to this paper that we published last year, which looked at growth in infancy and childhood and its association with age at menarche in 5 low and low middle income countries. All right. And the reason why we're doing this study is because of two public health interests. Okay, the first interest is this concept of age at menarche and the decline in the age of menarche, which is the time of the first menstrual period. And we know from data that it has been on a decline. It has been reducing over time and influenced by nutrition and other conditions, in society that we live in. So, for example, data from South Africa show that the age of menarche, reduced from around the age of 15 years old, the first time on average that young girls experienced menarche, experienced a menstrual cycle was around 15 years in the 1950s. Today, it is an average of around 12 years, all right? And the reason why this is important is because early age at menarche or early puberty is associated with, with adverse health conditions, such as higher risk of obesity, as well as adverse behavioral attributes, such as early onset of sexual activity, for example. The other public health interest that is aligned to this paper, if you look at the topic at the title, is this concept of early childhood growth. And when we're talking of height, for example, we're interested in improving growth in height in populations in low and middle income countries, so that we can reduce the prevalence of stunting. A large burden of the prevalence of stunting is, or undernutrition, is in low and middle income countries. And, regions like sub-Saharan Africa, for example, have struggled to reduce the prevalence of stunting, which has remained at around 40% over the past few decades. Whereas in other regions of the world, they have been successful in reducing the prevalence of stunting. In South Africa, it's still high at around 25%. And in a 30-year period, it has really not moved much. It moved from around 30% to around 25%. So there was only about a 5% decrease in the prevalence of stunting. And stunting is associated also with poorer health outcomes, such as poorer cognitive outcomes. All right. Now, there's what influenced this analysis for this particular paper is this concept of a critical weight that suggests that, once children achieve that critical weight, it may trigger the onset of menarche. But there's also contrasting evidence which show that females who are lighter at birth may experience menarche at an earlier stage compared to those who are born heavier. And this is attributed to potentially a faster gain in weight in that early infancy period among those who were born lighter. So, but another study in the Philippines showed that girls who were tall and lighter. So, if you think about this concept, all right, of faster weight gain among those who were born light. So, taking that concept and looking at children who are lighter, all right, so they are less than 3 kilograms, all right. So if you just focus on that group and you look at how height the length in those children influences the timing of age at menarche. In this particular study, they found that those who are taller and lighter had a 6-month earlier age at menarche compared to those who are shorter and lighter. All right. So, and I've said here, both groups were light, and they were born light, and they potentially experience fast weight gain. But the difference here is their length at birth. Those who are taller seem to have, earlier age at menarche, and that contradicts what we would like to do in terms of a public health intervention, which is to improve the heights of children. Remember, I said we want to reduce the prevalence of stunting by, improving the heights of children. But if this data are showing us that the children who are born taller more likely to have earlier menarche compared to those who are born shorter, what does that mean, all right, in terms of our public health messaging? And this is just shows the sample that we used for this particular study. We ended up with complete data of close to 4,000 individuals, all right, and we had a sort of a cascading process of eliminating individuals from the final data set. And I must specify that one of the requirements that, one of the things that I was required to do when I was writing this paper was to compare this group to, the ones that were not included in the final analysis to see whether there's any bias in the final sample. You can go ahead and read that paper to see the findings. But these are the general findings that we found in this particular study. This will be, like I said earlier, your first your first step in terms, or rather, it's the second step in this particular in the presentation as I was giving. I've done my exploratory analysis, but in terms of the statistical analysis plan, the first thing that you want to do is to describe your sample, right? You may want to describe both your demographic characteristics and you may also want to describe your clinical characteristics. Here, I've got maternal characteristics about this sample that I described, such as age, education, and height, and these being measured in a continuous fashion. I summarize them as means and standard deviations. So all of these variables up to z-score were summarized as means and standard deviation, as they were all continuous variables. But here, the prevalence of stunting, which is the number of children who've got a high z-score less than -2 of the World Health Organization standard, all right? That is a percentage, how many children compared to the total sample in the different countries had that z-score less than -2. And we worked out a percentage, which showed that, which showed us the percentages in the different countries. And here we also categorize, so this was our outcome variable, which is age at Menakim, and these are our exposure variables, which is this is your childhood growth characteristics, because we're interested in seeing how childhood growth influences your age at Menakim. Now, this is just one of the regression outputs that we had from this particular paper, and the final, in terms of the conclusion that we reached in this particular study. So if you're looking at, for example, we categorized, and I'm going to show you that in the script that I'm going to demonstrate right now. We categorize this growth in the early period to in line with birth weight and the rate of growth in height. All right. So looking at whether they are born light or heavy, and whether they experience fast growth or slow growth. All right. So you've got children who are born light and experience slow growth. They were born light and experienced fast growth. They were born heavier and experienced slow growth. And they were born heavier and experienced faster growth. All right. So we ended up with those 4 categories. And we're comparing using this one as a reference, meaning you're born light and experience slow growth. All right. What we showed was that, for example, if you're born heavy and you experience fast linear growth, you are likely to have so this is adjusted for maternal schooling, because maternal schooling was different between those between the countries, and it may influence our outcomes. It was associated with both the outcome as well as the exposure. So it's a confounding variable. All right. So we needed to adjust for it. All right. So we showed that yes, being born heavy and experiencing fast linear growth is associated with an earlier age at Menakim. And being born heavy, so this is now in mid-childhood. All right, so this is fast growth between birth and 24 months. And this is between 24 and mid-childhood, which is about, let's say, 5 years. All right, so being heavy and experiencing slow growth in terms of weight led to a this is weight categories, and having slow growth weight gain up to mid-childhood was associated with a delayed age at Menakim. Now, I'm not going to go into this for now. Maybe I'll come back to this. I'm going to escape, and I want to just come to this demonstration that I was talking about for the next 10 minutes or less. All right. So in Stata, you've got this file, which is called a do file. And this is what you can use to demonstrate your analytical process. This is a script that you can use to demonstrate your analytical process. For SPSS, you've got the SPS syntax. I find it more complicated compared to, so the SPS syntax for me is slightly more complicated compared to a Stata syntax. So this I prefer, but I do also use R, and I prefer those two, R and Stata. For ease of reference, I'm using Stata for today's demonstration. Now, in Stata, so the first thing that I do, obviously, I specify the directory where my data are located. All right, they are in my iCloud Drive. They are in my documents, and in the academic papers. And the paper there's a folder called the Menaki paper. All right, so that is where I find my file, and this is a file that I'm interested in. It's a DTA file, meaning that it is a Stata file. Now, what this do file allows you to do, I mentioned earlier that the characteristics or the elements of an analytical script, you need to have your different sections, and also you need to have your notes. How you write notes in a Stata do file, you need to use this the slashes, this forward, I think this is a forward slash, and this helps me to specify the sections and the different subsections in the data. So, for example, the first section here is data management, and under data management, I've listed all my variables. And the variables that I'm interested in are the maternal characteristics, the outcome variable. So this is the continuous age at Menaki, as well as the categorized age at Menaki. All right. And it was categorized using the mode in this particular case. So we worked out the mode of mode. Remember earlier I spoke about 3 measures of central tendency: the mean, the median, and the mode. So the mode is the most frequent value in a particular data set. So how many children reported, for example, if you've got more children that reported that they had their first menstrual cycle at age 13, so your mode will be 13. All right. So that is what we used in this particular case. And then the explanatory variables, or the independent variables, the relationship that we're trying to establish here is whether early growth is associated with age at Menaki, meaning fast growth is associated with earlier age at Menaki. And I've got those as my explanatory variables. I left out some here, which are the final ones that I used in the model. I'm going to show you those variables as they're important. They highlight an important concept rather, and that is a concept of multi-collinearity, which I'm going to explain shortly. So I listed my variables, which was 1.1. The next section was to compute variables that I need in my analysis. So I needed to generate the growth categories in relation to birth weight, as I showed you in the analysis. So, for example, the children who are born lighter and they experience fast growth, and the children or they experience slower growth, and the children who are born heavier and they experience fast or slower growth. So this is what is happening here. I'm generating these growth categories, all right? And this is still part of the same thing, all right? Here, This is just growing fast, all right? So yeah, so this code is generate, yeah, so this is about just about whether they're growing fast or not. And then I also use then the birthweight status, which is either born lighter or heavier, and the fast growth, all right, which I generated here, all right. So this is part of the data management of the data computation that I did for this particular study. All right, so I'm not going to get into those details. So the next level, as I said in my presentation, is exploration. All right, you want to explore the data. All right, and say for example, you've got in this particular case, you've got a so I've imported my data. Let me show you. I've imported my data already into Stata, and these are my data, and I can show you with the view that these are the data that I'm using. All right. So these are all, I mean, I did not use all of these variables. Some of the variables were used for other papers, but I'm not going to get into those. All right. So now I'm interested in exploring my data, and it is this section here. All right. So the first thing, for example, that I can do this for other continuous variables as well. I'm interested in seeing whether there are any outliers, for example, in this data. And I'm going to use this plot, which is called a box plot, which is very useful for comparing a continuous variable between different groups. All right. So if I run that, and to do that in Stata, you just need to highlight. You don't need to highlight everything. You just need to highlight, the row that you want to run. Maybe one letter in that row, and you click execute, and it's going to show you this plot. So this is a box and whisker plot. You've got the whiskers, and you've got the excuse me, the box and the whiskers. All right, and there is your median, and you've got your lower quartile, your quartile 1, and you've got your quartile 2, and you've got the maximum value and the minimum value. All right, and as you can see, so the median here for Brazil is around. Okay, I should have done this. So this is probably around 11. For South Africa, I know it's around 12. All right. This is Cebu in the Philippines. This is India. This is Guatemala. All right. And this is helpful to see if there are outliers in your data set, and then you can go back and deal with this. If they are not true values. You may also be interested in looking at scatter plots, for example, that show you a relationship between two continuous variables. So this is, weight for age, z-score. I mean, here it shows that, over the different, there's not much change in what do you call this? In age at menarche over the range of the z-scores. You can do that these are the other variables that I used in my analysis. And so I'm just demonstrating to you, especially when you're dealing with with continuous variables, some of the plots. Now, as I said earlier, now, one of the things, considerations that you need to have to make is whether there are any relationships between your variables, especially your explanatory variables. And using, a correlation, you can establish whether there is a relationship. So that tells you, this gives you the correlation coefficient. So what you can see here, I mean, this is the relationship of the variable with itself, but you've got, the relationship of height at age 12 with height at age 48 months. So this is 12 months and 48 months with weight at 12 months. Obviously, you expect that the individual's heights will be correlated. So individuals, the same individuals at 12 and their heights at 48 months will be definitely associated, related. And this is one of the important considerations for running a regression analysis, for example. I showed you earlier here. So I didn't speak to it. So there are different assumptions that you need to consider for regression, and those relate to the error terms, all right? And that all the residuals in simple terms, all right? And it's the assumptions of symmetry, assumptions of normal distribution, assumptions of homogeneity in terms of the spread across the model, as well as the independence of the error terms. So in this particular case that we're talking about, this here is violated, the independence, all right? And in summary, this is what you can summarize. This is how you can summarize what a regression, the expectations of the assumptions of a regression model is that the error terms are independently and identically distributed, all right? So in this particular case, we have variables which are correlated in terms of both being measured on the same individual, but also you've got meaning rather over time on the same individuals, but also you've got height and weight which are related, meaning as your height increases, your weight will also increase, all right? And those are showing relationship with your age at Menaki. All right. So this demonstrates clearly. So your correlation coefficient ranges from -1 to +1, with any value closer to 1 being a strong correlation, and any value closer to 0 is a weaker correlation. All right. Let's see if these correlations are significant. Again, as I mentioned earlier, I'm not, getting into describing the different methods. Correlation is just one of the statistical methods, and it's not within the scope of this webinar to get into those details about correlation, t-test, and so on. All right, so I'm interested in finding whether these correlation coefficients are significant, and it tells me, and it gives me a p-value if I'm testing at a p-value at a significance level of 0.05. So if the value is less than 0.05, if I'm testing at a significance level of 5%, if the value is less than 0.05, that means that it is statistically significant. And the values, as you can see here, even less than 0.001. I mean, they're 0.00000. So they're highly, highly significant, meaning that these variables are highly correlated. Fortunately, for us in this field, particularly, there are variables that have been developed which address this issue of both of correlation, both in terms of autocorrelation as well as multicollinearity. All right. Autocorrelation happens when measure values or measurements happen longitudinally. All right. And so there are these conditional values. So maybe let me just run a correlation coefficient, run the same test for these conditional pairwise for these conditional values. All right, and this is the z-score, and I want to see if there's any significance in terms of their correlation. Okay, let me remove that. I think it should be 0. Let's see. Okay, sorry, just give me 1 second. Let me try and find that variable. Here it is. I'm just machine the WHO. Okay. Let me add that here. So these are the variables that we generated, to try and deal with this correlation that you are seeing here. All right, let's see. And I mean, they should not be correlated, otherwise there's going to be a problem. What is happening? Okay, okay, let me see. Maybe on just the variable names. I just need to find them. Okay, here we go. Conditional weight gain. Conditional 2 to 4 years. 0 to 2. Okay, yeah. All right, so it's this one, and this one, and this one, and this one that I'm interested in. So these are conditional weight gains between 0 and 2 months and between 2 and mid-childhood, as I explained earlier. I'm going to replace that with that. Sorry, apologies. WHO 0. So let's see. All right. Now these are the correlation coefficients, and the p-values from this correlation test. As you can see, these p-values, if the p-value is greater than 0.05, in this particular case, it is not significant. If you're testing at the 95%, at the 5% level of significance, if you're testing at the 10% level of significance, if they're greater than 0.1, if you're testing at the 1% level of significance, if they're greater than 0.01, then they are not significant. These are closer to 1. So there's definitely no correlation between these variables. Even the weight change between birth and 2 years and between 2 years and mid-childhood, they are not correlated. So you've dealt with both multicollinearity, meaning that the variables are correlated, and also the issue of autocorrelation, meaning that the variables are correlated over time. All right. And different variables in different fields there are different approaches rather to dealing with this issue of autocorrelation of multicollinearity rather, in different fields. And autocorrelation, you can also deal with it using multi-level models. And this is just the script, as I was saying to you, showing you, I was explaining to you earlier. So, I want to, for example, compare, this is for maternal age, and I wanted to see if there are differences across the different regions, and I would I've organized my script to relate to the different tables. And as you can see, this is exactly how I've presented my data. Maternal age, I've got the maternal characteristics, I've got the child growth characteristics, I've got age and menarche right at the bottom. And if I just run that, for example, that gives me this output here gives me the mean age and the standard deviations of as well as the sample sizes for the different regions. So I've got 5 regions, as I said earlier, and these are the different mean ages. And right, at this stage, I'm not interested to see whether there are differences or not. I'm just interested in presenting these characteristics. All right. I may be interested in another study to see whether these are significantly different. So, for example, let's talk about let's look at maternal. Let's look at. I said maternal education is a confounder, and so looking at this, I'm going to add here another argument. I think I've got the spelling correct. I hope I've got the spelling correct. So I'm just going to run that. Yeah, it is correct. So I said maternal education is a very important. Maternal education is a very important subject, a variable in this area of social and life course epidemiology, because we know it is associated with better outcomes, both in terms of child growth as well as in maternal health. So here we show the number of years of education in the different regions, and these are obviously different. So the overall ANOVA shows that there's a difference, but I'm also interested in to see who is different from who. All right, Brazil versus Guatemala versus South Africa. So it tells you that there's a difference of 3 years of schooling between Brazilian women and South African women who were enrolled in this particular study, with South African women having more years of schooling compared to Brazilian women. All right, and which is why it was important for us to adjust for maternal schooling in this particular analysis, because it is associated with both the exposure and the outcome. And then I'm just going to try and rush now. I'm just want to show you the further steps that we took in terms of the analysis, and that is to compare. We ran a t-test to compare between standard and non-standard, to compare between yes, this is compared to, no, this is supplementary table between standard and non-standard children. And this one here was comparing those who were included to those who were excluded from the analysis. And supplementary, the figures that I generated, I just wanted to show you the regression. Yes, okay. So when I run the regression, all right. So I was showing here the nodes, the importance of nodes, all right. So I ran this. Let's see if it will run. Okay. Log min. Okay, there's a oh, okay. So after so I had a log I generated the oh let's generate it. This is a logged agent menarche. Let's just run firstly a histogram to see what agent menarche looks like. To justify why we needed to log it. So maybe, and I'm just running overall. I can't remember. So it's, I mean, it's it's high ketosis. The peaks are very high, but also in the different groups, it may be that, the distribution was not uniform. All right. So here I generated this variable, which is the log transformed agent menarche, and then this is the one that I use for the regression. Okay, it is running, and I'm not going to get into the interpretation of the output here, but what I wanted to show you is these tests that I run afterwards, after running my regression. I'm interested to see whether I, for example, one of the important assumptions I mentioned earlier around the error terms, which I've now extracted from this model. I want to see whether there's a sort of uniform distribution of these error terms here. And this is the type of you would expect sort of to be to be around zero, to be symmetrical, meaning you've got similar above zero and below zero. But here you've got more or less a lens type of shape. And if you look at other types of plots, like your Q plot, for example, well, it shows that it's not too far off, from this straight line. There is some changes at the tails, and maybe you want to explore what those values and then deal with that. So I'm going to stop it there at this moment. I know I didn't deal with what regression is, and what how you interpret a regression model and so on, but we wouldn't have enough time to get into that. But I needed to show you from the principle of transparency how you can build up your process, and also, like I said, I think yesterday or last week, this helps also in terms of dealing with reviews, to show what I've done, and that helps with transparency of my research. So I'm going to stop sharing and take any questions if there are any.